Welcome to the session on efficient MPC constructions. This is going to have 4 talks. There will be a track switching break after the second talk. The first talk is going to be sublinear communication, secure multi-party computation does not require fully homomorphic encryption. This is by Elette Boyle, Geoffroy Coteau, and Pierre Meyer. And Pierre is going to give the talk.
Just checking something out. Excellent. Hello, everyone. Thank you all for coming, and welcome to the session on not so efficient MPC. I'm here to tell you to talk about how sublinear communication secure multi-party computation does not require fully homomorphic encryption, which is joint work with Elette Boyle and Geoffroy Coteau. Now, what I mean by not so efficient is that you should in no way think of our scheme as being concretely efficient. Let's say what we're trying to do is we see fully homomorphic encryption as a very heavy hammer for the problem of MPC, and we're asking the question, is this really required, or can we do without? Now, first of all, what do I mean by sublinear communication secure computation? Just think of the 2-party setting for now. Alice and Bob wish to compute some fixed circuit C of their inputs, and they wish to perform the computation without having to trust each other with their inputs. Now, we know how to do this. We have protocols to achieve this since the 80s, but the communication required scales with the size of the circuit. So you'd have to communicate for each gate in the circuit. And since most people would agree that communicating is hard, we'd like to ask, can we save on communication? And specifically, I'm interested in whether we can go beyond the gate-by-gate approach and achieve secure computation with only a sublinear amount of communication. Now, there are 2 big families of protocols in this setting. Either you consider specific tasks, like some specialized circuits, for instance, private information retrieval, or you aim for a class of general circuits. And our work is very much on the in this second side. Like, we'd like to do as wide a circuit class as possible. Now, for technical reasons, basically we're stuck at low-depth circuits, and I'm going to explain what a layered circuit is in just a minute, and what's the relationship between the 2. But in case you're interested in the specific MPC model, think of semi-honest adversaries. Everyone will be following the protocol, even corrupted parties, and all but one corruptions. Now, what is a layered circuit? This is the circuit we're trying to compute. Well, a circuit is said to be layered if you can put the gates into layers, and the wire doesn't jump through the circuit. It only goes from one layer to the next. And now, why these structured circuits are nice for us is that you can always break down computation into small, say, log-depth chunks. And trust me on this. If we know how to do very low-depth circuits, but arbitrary circuits, very low depth, with a very small amount of communication, this translates into breaking the circuit size barrier for arbitrary depth layered circuits. So the question is, do we know how to do sublinear secure computation? For now, 2-party setting. The answer is yes, and until recently, we had 3 different ways of doing it. Now, if you use fully homomorphic encryption or homomorphic secret sharing, you'll get computational guarantees. And if you use correlated randomness, you can achieve information theoretic security. And in turn, these 3 paradigms yielded protocols from a variety of different assumptions, computational or otherwise. Now, this was the state of the art until recently. And so we'd say, we have many ways of achieving secure computation, sublinear secure computation, sorry. But we asked ourselves, can we build a tool which is a lot more focused on achieving sublinear secure computation? Which led us last year to introduce the object of correlated symmetric pair, which I'm going to explain what it is in just a minute, because we're going to use it today, and I guess it's not a standard assumption yet. So, okay, first of all, what is symmetric pair? I guess most of you are familiar with this. Alice, yes, in this case, Alice is the client. She has an index, and Bob has a database. And the goal is to allow the client to retrieve the element of her choice in the database in a private manner. Now, I'd like to just what's perhaps a tiny bit less standard is this notion of symmetric privacy, which simply means that you would want the server also has some privacy guarantees in that the client only retrieves a single index. But yeah, and you can see this as a very specialized form of secure computation. Now to our primitive, correlated symmetric pair. I want to emphasize that this is a two-party primitive, as in you have a single client and a single server, but that they would like to be doing a bunch of symmetric pairs in parallel. And this correlated part is that the client doesn't want to retrieve arbitrary indices from all of the databases, but like all of the queries are highly correlated in a public manner, and you would only want to pay the communication, to pay a cost of communication proportionally to the entropy of the queries, not to the concatenated size of all of them. If you think about it for a minute, using rate 1 FHE, you can do this. But what we showed last year is that you can, in fact, do it from a primitive which is morally much closer to linearly homomorphic encryption, which is good news if we're trying to get rid of FHE for the task of sublinear secure computation. So we'll be using this primitive a bit later in the talk. But now let's go back to the set of assumptions which are known to imply sublinear secure computation. I'm forgetting about the correlated randoms for now, because since in that model we're not counting the communication necessary for the setup, it's more about sublinear online communication. But so basically we have three different ways of breaking the circuit size barrier from computational assumptions. And all of this was in the two-party setting. And you can ask yourself, what about the multi-party setting? And unfortunately, we don't know much, or at least we did yesterday, because what we're going to show in this talk is that if you combine the two objects that were only known to yield two-party computation, then there's a way to put them together and achieve multi-party secure computation with sublinear communication, which was previously only known from FHE. So a bit more formally, what are the results I want to talk about today? So I want to expose our framework, so the protocol, which does not use FHE, and in turn it can be instantiated under concrete assumptions for 3, 4, or 5 parties. So first of all, I'd like to emphasize that we use two tools. We're putting together two tools to achieve n+1 party computation. The first is an n-party primitive, and the other one is a 2-party primitive. So there's really, we're not cheating in order to achieve n+1 party. And as I said earlier, the class of computation we'll be handling is either log-depth circuits, or layered circuits via the transformation that I showed earlier. Now, for the most of this talk, I'll actually be focusing on log-depth circuits with very low communication. What I mean is essentially optimum, so basically like linear in input plus output size. But I'll be going back and forth. So if I say optimal communication and sublinear, it usually means I'm thinking about one of the two settings, but it's the same thing. So what is this template? So you have to read this from top to bottom. Let's not think about efficiency at all for now. Let's just see how things work. So you have n+1 parties. These are the circled, P0, P1 to Pn. And they're going to play different, P0 is going to play a special role, and P1 to Pn have symmetric roles in the computation. So these boxes are ideal functionalities. You can think of it as just some computation providing the guarantees written inside the box. So first of all, let's say you want to compute the circuit C, which has n+1 set of inputs shared between the players. So what P1 and P-n are going to do first is going to send their input into the box, which is going to hard code their inputs into the circuit and secret share that function. So for now, think of a naive secret sharing, just take the truth table and secret share it additively among the parties. So now each party Pi holds some share of the function Fi. So you can either see this as a function share, or like I do it, like I like to think about it, you can think of Fi as being a function which on input x0 gives you a share of f of x0. But you can also see it as just simply a share of the function f. So now that all of the parties P1 to Pn each have their share of the function in which they hard-coded their inputs, they each pairwise perform an oblivious evaluation with the last party P0. So what's an oblivious evaluation? It means that P0 holds some input, and each party Pi, the other one, holds some function. And the goal is to allow P0 to evaluate the other party's function on exactly one point, and in this case, on x0. So hopefully it's simple enough that we can intuit why this is secure. So let's say you only corrupt a subset of the parties P1 to Pn. Because you do not have access to all of the function shares, you don't know anything about the inputs which were hard-coded that you didn't already know. And even if you also corrupt P0, the last party, because of the oblivious evaluation, the only information you know about a function share that you did not already know is a single evaluation, and the single evaluation is the output share which you are always allowed to have. But now this protocol it's sort of underspecified. It's more of a template than an actual protocol. Why? Because I said, okay, assume we have a way to secret share a function, and it's unclear that this can even be done in polynomial time, and even less with polynomial computation or sublinear communication. So in order to do that, we need a tool known as function secret sharing. And the high-level idea is simply we want to be able to succinctly generate these shares of some secret function. So formally, an FSS scheme is a pair of algorithms, FSS-gen and FSS-eval. So just to be explicit, the goal is to be able to secret share a function, such that, and then you can evaluate the function shares on some public input in order to get each party can get a share, and then you can reconstruct. Now, you can think of function secret sharing as a way to compress these function shares down to tiny keys. In particular, every party on the right, like using function secret sharing, gets an evaluation key. So that's one of the KIs. And if you hard code the evaluation key into the FSS evaluation algorithm, then you can think of this function as being a share of the function f. Okay, so now that we've seen how a function can be secret shared somewhat efficiently, let's see what it looks like in our template. So I haven't done anything except I've said instead of generating shares of the function, I'm distributing evaluation keys. And then instead of obliviously evaluating a function share, I'm obliviously evaluating the FSS evaluation procedure. So Eurocrypt at this point, I claim that if I am given an n-party function secret sharing scheme such that all of these boxes can be done with low enough communication, so specifically what I need is a function secret sharing scheme whose key generation procedure can be distributed efficiently. It's first condition. And second condition, such that the evaluation keys can be obliviously evaluated with low enough communication, then overall, we'll get a secure computation protocol for the n+1 party circuit C with overall optimal to very low, sublinear, depending on how you think about it, low communication protocol for C. Now the question is, can we build such an FSS scheme? And if you think about it, I said there are two main properties I need to address: the key distribution and the oblivious evaluation. Now, since keys are fairly short, it's perhaps not too surprising that this procedure can be done efficiently. Oblivious evaluation, on the other hand, since evaluation can be as hard as the original function, the original circuit we're trying to compute, that's the key step. And basically what I need here is a very specialized two-party computation protocol with sublinear communication complexity. And in fact, we're going to use the tool I presented earlier, correlated symmetric pair, in order to instantiate this very highly specialized this highly specialized oblivious evaluation. So let's say you have a function g with two sets of inputs, one for Alice, one for Bob. And what happens once Alice hard codes her own inputs in there? So now the setting is Alice holds a secret function, and Bob holds an input. Now, under the assumption that this secret function with Alice's input hard-coded has low depth, log depth in Bob's input, can we do oblivious evaluation of this circuit? And the answer is yes, using the simple observation that because I'm dealing with a circuit like where every gate, be it an addition or a multiplication, has fan-in at most 2, each output in log depth only depends on at most logarithmically many inputs. So in turn, each output gate of your circuit has a polynomial-sized truth table. And now in order to evaluate this circuit, what you can do, you can have Alice prepare all of the truth tables, they're all polynomial size, and retrieve exactly one element from each of these databases. And these queries are highly correlated. I told you correlated symmetric pair was a public correlation, so that's the topology of the circuit, on some joint entropy, some joint secret of Bob's. And Bob's, the entropy used to describe all of Bob's queries is simply his own input to the circuit. So using correlated symmetric pair, we can instantiate with essentially optimal communication this oblivious evaluation procedure. So if I now plug this back into the template, to the n-party FSS template, all I've done here is like I said, okay, it used to be oblivious evaluation of the FSS eval. I'm going to use correlated S pair. So now the condition is, can I build an n-party function secret sharing scheme with efficient key distribution and such that the evaluation can be done in low depth? Oh, the question is, can I do this? So if I need FHE at this point, this was all for nothing. And the answer is yes. I know how to build such an FSS scheme if the circuit I'm trying to compute is low depth. And in turn, this yields a protocol for layered circuits. Now, what I could do is simply give you the FSS scheme and show you how to instantiate the key generation procedure and the evaluation procedure. But instead, I'd like to go back to the original framework, without even the FSS abstraction. And now, with the hypothesis that I'm trying to compute a low-depth circuit, log depth circuit specifically, can I come up with a direct grounds-up approach? Now, just to remind you, this is the original template, and because I need space, I'm going to put it in a corner. So the first assumption is, how do I secret share a function? And the first assumption I want to challenge is, we are no longer thinking of secret shared truth tables. However, the observation we made before is also true in this setting. Right? If you have a low-depth circuit, it can be represented by a bunch of polynomial-sized truth tables. So how I'm going to secret share the function is I'm going to make sure that each party pi from p1 to pn is going to hold additive secret shares of these truth tables. Now, how I'm going to do it, I'm going to be very quick on the details, but basically I'm going to use a tool known as homomorphic secret sharing. Now, just think about this. You can either trust me that there is a way to generate these secret shares of these truth tables, or if you want a bit more detail, assume you have access to a secret sharing scheme with some homomorphic properties. So the parties P1 to Pn are going to generate secret shares of the vector of inputs, x1 to xn. And then, now that they have their shares, they're going to perform some homomorphic operation on the shares in order to homomorphically compute the function which on input x1 to xn generates these truth tables. And while this is not entirely trivial, it's not necessarily very important to see the details at this point. So using the n-party primitive of homomorphic secret sharing, we can make sure the parties hold additive shares of the truth tables. And now we can use correlated SPIR to allow Bob to perform the oblivious evaluation. And this is essentially how n-party HSS and the two-party primitive of correlated SPIR allows you to not require FHE while doing sublinear secure computation for log-log depth circuits. Now, if you wanted to, you could try and parse this and try and identify where the n-party FSS is with log-log depth evaluation, whatever what we talked in the first part of this talk. But you can also see this as a direct and standalone construction. So to summarize, we have a general framework with sort of abstract properties, assuming we can secret share a function efficiently and evaluate, and some specialized protocol to evaluate it. We get sublinear secure computation. And because of structural properties of log-log depth circuits, we can instantiate our framework using n-party HSS and correlated symmetric pair. Now, if you don't know about HSS, you'll have to trust me that we have all of these assumptions. We have it under all of these assumptions. And if you do know about HSS, you might be wondering, wait a minute, we don't actually have four-party HSS from DCR, and we don't have two-party HSS from DDH. Which brings me, I'll just mention very briefly some secondary contributions. The first thing is that I don't actually need the full power of homomorphic secret sharing. It's perfectly all right.
We are almost out of time. So
OK, great. It's
finished.
One slide. Yeah. Thank you. Assuming my HSS has a lot of errors, it's still enough. Yes, even if my HSS has errors, we call this Las Vegas HSS, my framework still goes through. And in particular, this is why we can get an instantiation from DDH. And how do we get four-party HSS from DCR? There's a very simple extension of a known four-party HSS for constant depth correlations, which we can extend to fit our needs. So I don't know if you have any questions for me, but while I thank you for your attention, I'll leave these questions up, because as these are the questions I have for you, if you want to try and extend our result. So in one sentence, what is the conclusion? Is that we can now break the two-party barrier for sublinear secure computation without fully homomorphic encryption. So thank you for your attention, and I'm happy to take any questions if there's time.
Yeah, maybe we should go to the next talk because we are a bit over time.
It was a sublinear communication, but superlinear length, right, of the talk. Okay.
The next talk is actively secure arithmetic computation and vector OLE with constant computational overhead. This is a talk by, or this is a work by Benny Appelbaum and Yves Constantini, and Benny is going to give the talk.
Yeah, thank you. This thing works? I'm not sure. Okay. Good, so this is joint work with my student, Niv, who couldn't be here, unfortunately. And that's a good opportunity to mention that we have a very nice crypto group in Tel Aviv. And we recently got an ERC grant, a new one, so we have available positions. So if some of you are interested, please contact me. Good, so in general purpose secure computation, we typically get a function that we want to evaluate. And the classical setting is that this function is given to us as a Boolean circuit. However, in the real world, typically we are interested in numerical computation, right, over the integers or over real numbers. And in principle, as we all know, we can translate this kind of thing into a Boolean circuit. This translation is typically costly. Right, yeah. So these are Yuval's slides from the ADINZ paper, I think. Okay, so a better alternative is to use the arithmetic circuit. So we think about our items, our data items, as being taken from a large finite field, and we're going to manipulate them by using addition and multiplication. And indeed, once you have this kind of notion, you can easily translate it, translate computation even over the integers or over the real numbers by using a sufficiently large field. So this is the goal in this work, to try to understand what is the computational cost as opposed to communication cost in the previous talk of evaluating or securely evaluating an arithmetic circuit. Okay, so that's the goal. And we're going to use this very clean model of arithmetic black box in which the protocol has in the black box access to the field. And we're going to measure complexity by just counting field operations and measure communication by the number of field elements that are being communicated. Good, so what do we know about this model? So a few years ago in crypto, with some respected colleagues, we have this result that shows that if you want two-party secure computation with passive security, then you can get it with a constant overhead. Meaning that if you're given an S-size circuit, you're going to perform only order of S arithmetic operations, plus something which is polynomial in the security parameter. So if the circuit is sufficiently large, you pay a constant computational overhead per gate. Now, to prove this result, we had to introduce this primitive, which is now kind of popular, the Volet primitive, which is, roughly speaking, a vector by scalar multiplication. And we show that this can be implemented with a constant overhead and even constant number of rounds. And then we kind of compile it into a protocol for general circuits. And these protocols have several nice properties. They make, as I said, a black box access to the field. We use the OT hybrid model, which means that we are going to use oblivious transfer, but we are going to use them in a black box way. There are many reasons to want this feature. Most notably, if you don't have this feature, then you are likely to be completely impractical. Moreover, we rely on the arithmetic variants of well-studied assumptions. Concretely, to get the Volet, we used an arithmetic version of Aleknovich, which roughly speaking says that this is the assumption that noisy code words are pseudo-random, where the code is generated by a sparse matrix and the noise is has constant rate. And for the other transform, we had to use arithmetic Goldreich assumption, basically a local PRG with a superpolynomial stretch. We heard about it yesterday. And as a bonus, we got statistical security against one party, even UC security if you want, and all these results I talked about the two parties, but it extends nicely to any constant number of parties. So that was ADINZ. And in fact, the protocols were sufficiently simple to be practical, at least in the Volet level. So they had concrete efficiency. They were even implemented. And this is nice because there are many direct implications of this tool, right? From a secure linear algebra to a non-interactive MPC. So the goal today is to try to get a similar result, but with active security, right? So that's the goal. And the first thing that comes to your mind is that let's use the previous protocol, right? I mean, we already worked on it. Let's throw in zero-knowledge proofs, compile it, and get an actively secure protocol. This is known as the GMW paradigm. The problem is that this thing will not make a black box access to the OT. We'll have to open the OT and make a non-black box access to the OT, which is a bad thing. So we want to avoid it. And the main result, at least the main theoretical result of this paper, is a protocol that achieves active security, constant overhead, and all these previous features. Right, so that is, we have given a circuit with S gates, we can compute it by making only order of S field operations. Again, black box access to the field, black box access to the OT, same assumptions as we used before in the passive setting, and also all these additional features. And this is previously we didn't know how to achieve it, even if you don't care about all these features and just care about black box access to the OT. Okay. In fact, even if you focus on the Volet primitive, the only known construction that achieves black box access to Volet and constant overhead is based on this compressed Volet approach, and it requires somewhat less standard assumptions, namely leaky LPN with a sub-constant noise rate and over less standard matrices, plus correlation robust hashing. but these days this is for free, I guess. Okay, so this is the theoretical result of the paper. On the practical side, we were trying to optimize the concrete complexity of Volley. Okay? And this is a different game. So here we are allowed to make more assumptions. And indeed, we introduced a new variant of the LPN assumption. I'll tell you a little bit about it later. It's a kind of a non-malleable version of LPN. I think that it's interesting for its own. And we got a concretely efficient protocol. We implemented it, Niv implemented it. And to the best of our knowledge, this is the first implementation of actively secure Volley over non-binary fields. We kept the same parameters as in the previous passive case, and the overhead is roughly 20% more than it was in the previous paper. We also introduced all sorts of new optimizations, like sparse LU decomposition. And just to give you some numbers, so the communication, we have 3 rounds of communication, and we communicate 4 field elements per Volley element, as opposed to 3 in the passive setting. In terms of computation, so amortization kicks in very fast. Even for 10,000 long vectors, we pay only 4 OTs and about 300 arithmetic operations, just additional multiplications. And in fact, if you look at longer vectors, then you'll get better constants. And furthermore, by using all these LU decompositions, we can push most of the work to an offline phase, which is non-interactive. Okay, so you can do it by yourself. And then in the online phase, it's extremely fast. I mean, the receiver just applies 4 OTs and 10 arithmetic operations, the sender 80 arithmetic operations. And this is kind of nice because we have Volley-based zero-knowledge proofs in which the verifier plays the role of the receiver. So it means that you get very fast verification in these zero-knowledge proofs. How does it compare with other work? So in the last 2 years, we've seen like amazing breakthrough using this compressed Volley approach. And in this approach, actually can achieve rate 1. So in terms of communication, it's better. But it seems that there the amortization kicks in a later point. And so this approach seems to be competitive for medium-sized vectors, especially when you have a fast network. And just to give you some qualitative intuition, most of the work in this approach is devoted to generating these short Volley correlations, namely, and this requires cryptographic operations, and here most of the work is just linear algebra, solving sparse equations. Right? There are no cryptographic operations except for the OT. Good, so I'm not sure how I'm doing with the time, but as long as you don't stop me, I will continue.
Yeah, you still have like 7, 8 minutes.
8 minutes, 9, okay. So I'm not going to talk too much about the proofs. I think that there are 3 interesting ideas. There are 2 of them in the Volley layer, and the third of one in the transformation from Volley to general circuits. I will not have time to say too much about the third one, but let me say a few words about the first and the second. So the core ADINZ protocol is what we call reverse Volley. So Alice holds the scalar and the vector, Bob holds the vector, and Bob should learn XA plus B. And you can think about it as a secret sharing of the product XA. Right? That's the way, that's a convenient way to think about it. And let me note that if Bob throws in the all zero vector, then he learns B. Right? It's zero, the X times A zeros out. Now, how does the protocol look like? Well, we have this linear mapping E. So Bob applies the linear mapping to his vector and add noise. This is kind of a ciphertext, sends it to Alice. Alice exploits the linearity. She multiplies this ciphertext by the scalar X, adds the linear operation over B, which means by linearity that you get this linear operation XA plus B, plus this garbage term. And we want to pass it back to Bob, but we have to be careful because if you pass it as is, then this additional expression will leak information on X. So to solve this problem, we use OTs. Namely, we are going to place this vector of Alice. Each entry is going to be placed in the one input of an OT. And then we let Bob choose which coordinates to get based on his noise vector. Okay, so that's basically the protocol. Now Bob learns this linear function, solve a linear set of equations, gets the vector. And of course, the interesting thing is to do all these things in linear time, but that was already solved there. Okay, so what happens in the malicious setting? So malicious Bob can simply ask for a noisy coordinate, learn X times the noise, and he knows the noise, so that's it, he knows X. So this is bad. So this protocol is completely broken. And the challenge is to somehow force honest behavior without knowing the noise vector. And in fact, the noise vector is not fully defined, right? I mean, maybe you can think about CAE as having different noise vectors, right? And we want to do it efficiently, linear time, and we want a black box access to the OT. So the first simple observation is that, in fact, we have a clean condition that tells us whether there was a cheating or not. Namely, if this vector, the selection vector of Bob I, satisfies the following linear algebraic condition, if you look at the vector C, the noisy code word, restricted to I, and check whether it's in the image of the linear mapping restricted to I, then you can prove that everything is okay. Okay? And morally, it means that there is no noise, right? I mean, we ask only for clean coordinates. And now, once we have this observation, the natural idea, which is not new, it was used in other contexts, similar contexts as well, is to use some sort of a generalized OT. So what do I mean by this? Let's wrap all these OTs with an additional layer that makes sure that information passes from left to right only if this condition holds. Okay? And the main contribution in this part is to actually implement this thing in a linear time. So we use kind of secret sharing tools, and it's not surprising because this condition is linear algebraic, and for linear algebraic conditions we have very efficient secret sharing schemes, right? If some of you know about span programs, so it has a very natural span program. And also this linear mapping is linear time computable by design. So this does not immediately mean that the secret sharing trick here is going to be in linear time, but after massaging things a little bit, you can make sure that this is a linear time. Now, something interesting that happens here is that in order to get all these properties, we actually have to give up a little bit. So yes, and the actual construction leaks information, even if the condition does not hold. In particular, it leaks the information about the vector B. But this is okay because in this concrete setting, it's okay to leak information about B because we can simulate it, right? I mean, the simulator can simulate all the information about B by letting Bob ask the ideal functionality with the O0 vector, right? So this is okay, and we can still simulate. What about the cheating Alice? So, in principle, Alice could do some crazy computation, compute some crazy D, and let's think about less crazy thing to do, like something relatively simple. Let's assume that she computes D as she should, but just add some garbage on the first coordinate. What happens here? Well, there is no privacy leakage, right? Because Alice does not get information back from Bob, right? All the information goes to Bob, but you can hurt correctness, right? And Bob, if he decides to ask for the first coordinate here, right, then he will see a noisy element, and will not be able to decode, and he will output bottom, say, abort. Now, this is annoying because this event of outputting bottom, it depends on the actual noise, right? And when we do the simulation, we don't have access to this noise, and we have a simulation problem. Okay? So what do? So we suggest three different solutions. The first solution is heuristic. Let's assume that everything is okay. I mean, we have a simulation problem. We don't like it as a theoretician, but we don't have any attack, right? And we tried quite hard. So although we don't like it, maybe in practice it's okay to say that the protocol is secure, and you can even formulate an assumption that says that the protocol is secure under this attack. I mean, it will be a little bit ugly, but it can be done. The second approach is the most conservative one, which is actually reduce security to the original assumption. And for this, we have to tweak the protocol, and we do some sort of a cut and choose approach. So we run many, many instances, going to open few of them, check if everything is okay, and then merge them together. And to make it linear time, we have to merge them efficiently. So we use a linear time computable exposure resilient function. And one cute thing about this approach in this specific case is that this cut and choose is silent, in the sense that when I open a session, Bob can open the session in a silent way without even letting Alice know that the session was opened. We don't have to add another layer to the protocol. This kind of happens inside the protocol by choosing A to be the all-zero string. And again, I'm oversimplifying things a little bit because you have to think about the modified protocol with the secret sharing, etc. But let's ignore this for now. And the third approach is to use this new assumption that we introduce. And this assumption, I'll show you it in a minute. With this assumption, we can add a small tweak to the protocol with very low complexity, and then we can actually prove that this is secure. So let me tell you about this assumption and conclude. So we call this the noisy-correlated code word assumption. It's the following assumption. So the challenger sends a noisy code word to the adversary. And the goal of the adversary is to generate a new noisy code word whose noise is correlated. Okay, so what do I mean by this? So the adversary wins if whenever the coordinates here are clean, also these coordinates are clean. And in addition, this vector is far from any scalar multiple of the original vector, noise vector. Okay? And if you remove one of these conditions, it's very easy to win in this game. But if you put them together, it seems to be hard. And indeed, we can prove, at least in the binary setting, we can reduce this assumption to standard LPN. We don't know, by the way, how to do it in the arithmetic setting. So this is kind of a nice thing to think about if you want. Let me summarize. MPC with constant computational overhead, not communication. I should say, of course, if the computational overhead is constant, also the communication is constant, right? This is stronger than just having constant communication. So in the Boolean setting, we have it by ICOS. In the arithmetic setting, we had to work harder, and we got it in ADINZ. In this work, we kind of get the active setting. Now, I said that moving from here to here was harder, and I showed that I can do this thing, so why can't I do this arrow? So that's maybe the take-home message. So it seems that at least in some cases, in the arithmetic setting, it's much easier to go from a passive to active security. Let me give you some hints. So we explored the linear algebraic structure of the protocol. That's already, I mentioned it in the secret sharing part. But one thing that I didn't show you, and this is kind of the hidden bullet, that the bullet number 3 that I had, is that we exploit the fact that the honest parties are low-degree polynomials. So let me explain shortly. So at some point of the protocol, we have a garbling, right, as usual, but it's an arithmetic setting. And we have the garbler, who is malicious, and we have the evaluator, which is honest. And we exploit the fact that the honest evaluator is a low-degree polynomial, the code of the evaluator, right, of this party. It's not about the evaluated function, but the code itself of the evaluator in the passively secure protocol. And for this reason, even if this guy goes crazy, eventually the output here is a low-degree polynomial, which means now that we can use all sorts of tricks about low-degree polynomial to cheaply compile this thing into the active setting. And that's what we do. And this is kind of cool because this is an unexpected feature of the arithmetic black box model. So many open questions. Let me just leave them on the screen, and thank you.
We have time for maybe one question. So, like your constructions are. Oh, okay. Sorry. No, please.
You can ask both. I mean, it's okay.
Okay, thanks. I just wanted to ask if you think your techniques carry over if you're in a ring setting, for example, modulo prime power.
I have to think about it. I'm not sure. Maybe in a ring where you have like a few zero divisor, like RSA rings, I can imagine that this thing can work. I'm not sure about a general ring. I have to think about it. Yeah, good question.
Okay, thanks a lot.
Yeah, I was going to ask also if these constants that you have, they depend on the field. So I mean, can they get smaller when the field is large or something like that? Or?
No. So it's independent of the field. That's one of the cool things. I mean, you can see in the paper we have tables, but the constants itself are independent of the field. We implement it over different fields, of course. When the field is large, then making 2 operations over a large field is typically more expensive. But actually, you don't like as long as it's about memory. As long as say 64 bits, things are extremely even 128 bits. It's kind of fast. Like.
Okay, so let's thank Benny again.
Thank you.
And I guess you have 4 minutes to change tracks.
I should have said.